The new chapter which we're going to deal for today's session is linear equations in two variables. What is a linear equation in two variables? Let's recap with the polynomials. We have discussed about the different types of polynomials, initially with linear polynomial, quadratic polynomial, cubic polynomial, quartic and quintic, etc. So proceeding the similar manner, we have now going to deal with linear equations which are very much connected with the linear polynomial. And since I have two variables, the condition is that the polynomial needs to essentially have the two variables x and y, of course. So let's see in brief about the linear equation and its two variables and its respective definition. Before we go into the definition, let's get into introduction on linear equation to recap with the linear polynomial. As we know that the polynomial function denoted by p of x with variable x is linear if it has its highest degree of the variable as 1. Say for example, I have this to be ax plus b. In this case, I find that the highest degree of x is 1 and hence such a polynomial is called a linear polynomial in x. In the variable x. So clearly seeing this linear polynomial, I find only one variable which is x and its power being 1. Therefore, the degree of this entire polynomial is 1. And such a polynomial with degree equal to 1 is called a linear polynomial in the variable x. Now let me connect with what could be the linear polynomial in two variables x and y. So to connect with the linear polynomial in two variables x and y. Let's see how we can define the respective definition of linear polynomial in two variables x and y. So let's reconsider the definition which says that a polynomial is linear if its variable is with power 1. The highest power is 1. Therefore, when I introduce the two variables x and y into the polynomial, then I clearly assume that I need to have both the variables with degree 1. So a linear polynomial in two variables x and y, unlike the one variable x, is defined to be ax plus by plus c, because each of the term has degree 1 with variable x here being degree 1 and this term equally having the degree as 1. Therefore, such a polynomial is called a linear polynomial in two variables. Here, this is a linear polynomial in one variable x, but because I have the introduction of two variables x and y, this is a linear polynomial in x and y, the two variables here being x and y. A linear polynomial in x and y defined to be p of x comma y equals ax plus by plus c, provided the condition a, b, c belong to real numbers. The three constants or the coefficients must be real numbers, and the rule 2 being a and b should not be equal to 0. They must be non-zero. A, B, C belong to R and A and B are non-zero real numbers is how I define the linear equation, linear polynomial in two variables x and y. Any example we can take for this would be, say for example, I have pxy is 2x minus 3y plus 4, then this is clearly with the first term being with degree 1, and coming to the second term, its degree also being 1, and of course the degree being 0. The highest degree for x and y is 1, and therefore this is a linear polynomial in x and y. Is how we define the linear polynomial. Now let's take an example problem where we do not have a linear polynomial. The contradictory to this example is what we are going to discuss continued. For example, I have p of xy is 4x minus 3x y square plus 4y minus 3. Let's see if this is a linear polynomial in x and y with xy. So let me just consider this example to investigate for whether this polynomial is a linear polynomial in x and y. So let's take the given example problem in which I clearly have my pxy to be 4x minus 3xy plus 4y minus 3. Now before I justify for its linearity in the polynomial, I have to search for the degree of each of the term. So coming to the first term, I have my degree of x, which is 1, of course, because x power 1. I have my degree of x, which is 1, and I have my degree of y, which is 1. Therefore, on the whole, I find this combined degree of the second term to be 1 plus 1, which is equal to 2. And next, I have my third term whose degree is 1, and I have, because its power is 1 for y, and then the constant term whose degree is 0 because there is no x or y attached. So x power 0 or y power 0 is what we assume. Therefore, I have, for the first term, I have this, and for the second term, I have 2 because the combined degree is 1 plus 1 for each of x and y, and then the overall degree for the second term is 2, and for the third term it is 1, and for the fourth term it is 0. Therefore, when I compare each of the degrees 1, 2, 1 and 0, I identify that the second term, which has degree 2, is not equal to 1. Now, because the degree is not equal to 1, the highest degree for the second term is 2. It cannot be a linear polynomial. For linear polynomial, degree must be equal to 1. The highest degree of the entire polynomial must be equal to 1. Degree 2 not equal to 1. Therefore, the given polynomial is not a condition, is how we understand the concept. So this is a linear polynomial in x and y, and this is not a linear polynomial in x and y. Now that we have discussed about linear polynomial, let's enter into discussing about a linear equation in the same two variables x and y. Linear equation in two variables x and y. Definition. So as we come across, let's recap with the linear polynomial, which is defined to be a polynomial p of x comma y is said to be a linear polynomial in two variables x and y if this is equal to ax plus by plus c, provided all the constants a, b, c belong to R and a not equal to 0 and b not equal to 0. Is how we define a polynomial with a, b, c belonging to real numbers and a not equal to 0 and b not equal to 0. So let's see how we can define the linear equation derived from the linear polynomial. So this polynomial p of x comma y equals ax plus by plus c is called a linear polynomial in two variables x and y if a, b, c belong to R and a not equal to 0, b not equal to 0. Now what is an equation? When does a polynomial become an equation? Is the biggest question in comparison. So as we see here, the linear equation is obtained when I equate the given polynomial to 0. So when I want to convert this into an equation, I just take this in the form equal to 0. That implies a linear equation in x and y is defined to be p of x comma y equal to 0, which is indirectly ax plus by plus c equal to 0. Therefore, a linear equation in x and y is finally concluded to be ax plus by plus c equal to 0, with a, b, c belonging to real numbers, as with the same condition as that for the linear polynomial. So a, b, c must belong to real number, and the second condition being that a and b should be non-zero real numbers, and a not equal to 0 and b is also not equal to 0 is how I define the linear equation in two variables x and y. Linear equation in two variables x and y. Ax plus by plus c equal to 0. A, b, c belong to R, and a not equal to 0, b not equal to 0 is how I define. For example, I take an equation in the form 2x plus 5y minus 3 equal to 0, then let's test whether this is a linear equation in two variables x and y. So initially I test with rule 1. The rule 1 is first to take with the given equation in the form equal to 0. Rule 1 is the degree is 1, and rule 2 is the degree is 1 because its power is 1 for each x and y. So first term the degree is 1, for second term the degree is 1, and for the third term the degree is 0. So the highest degree out here is one. Therefore, that is the rule 1 through which we identify it is highest degree in 1. And number of variables in this polynomial is x and y. Therefore, I have two variables being x and y. Therefore, the number of variables is 2, is the rule 2 which I identify in the given problem. The rule 3 is that the left hand side of the polynomial is equated or can be equated to 0. So left hand side is equated to 0. Therefore, on these three conditions, I can say that the given problem is a linear equation in two variables x and y. If I have these three conditions satisfied, therefore, the given equation (2x plus 5y minus 3 equal to 0) is a linear equation in two variables x and y, is how I understand the given example problem. Any problem given out there to be identified for linear equation in the number of variables, we first take the rule 1 in deciding the highest degree of each of the terms. Finding the degree of each term, we extract the highest degree. If the highest degree of the entire given expression is equal to 1, then it is linear. and here the highest degree is 1. Therefore, this given expression is a linear polynomial. Next is about finding the number of variables in the polynomial. Clearly, we identify the number of variables in the entire polynomial. The variables here being x and y, therefore the number of variables is 2, x and y. Therefore, I can now assume that this is a linear polynomial in two variables x and y, is how we justify. Thirdly, about identifying for the equation. Imagine that if I can write the expression in the form equal to 0, then I can say that the given expression being expressed as equal to 0 makes me clearly confirm that the given equation is a linear polynomial, a linear equation in two variables x and y. A polynomial converts to an equation if it is equated to 0. Therefore, the given equation 2x plus 5y minus 3 equal to 0 is a linear equation in two variables x and y, is how I conclude the given example problem. Now let's take an example problem where the given expression is not equated to 0 and justify if that is a linear equation in two variables x and y. So let's take an example problem to understand the concept more stronger. For example, I have an equation which says 2x minus 5y plus 4 equals 3 minus 9x plus 2y. Now this expression clearly makes me witness that this is not equal to 0. So do I call this a linear equation or do I call this an equation? Let's see how we can justify. Before we do this example problem, one thing is for sure that we need to justify only after the complete solving. Bring it to the most simplified form and then justify for a linear equation in two variables x and y. So let's take this example problem, investigate it. The given problem is 2x minus 5y plus 4 equals 3 minus 9x plus 2y is what is the given expression. So let me try to simplify this by taking all the terms to the left. As I can see that this can be further simplified by taking each of the terms on the right hand side to the left hand side. So 2x minus 5y plus 4 plus 3, when I bring it to the left, it is minus 3 minus 9x when brought to the left is 9x plus 2y to the left is minus 2y equals 0. So I have all the terms on the right which are brought to the left, equating to 0. Linear equation is always equated to 0. Now let's simplify where my 2x and 9x are added to give 11x. And minus 5y and minus 2y are added to give minus 7y because minus 5 minus 2 is minus 7. Then the constants here are added to get 4 minus 3, which is 1, equal to 0. So this is now the most simplified equation of the given problem. So let's see if this is a linear equation in two variables x and y, to be followed with the three rules. Rule 1, the degree of first term is 1, the degree of the second term is also 1, the degree of this is 0, therefore my rule 1 is highest degree out of all these is 1, therefore it's linear. Next, the rule 2, identifying the number of variables. I clearly see that there are two variables x and y. So I have two variables x and y and it is a linear, and as I see that the left hand side is equal to 0, that's the rule 3, my LHS is equal to 0, therefore it's an equation. And overall, I conclude that this is a linear equation in two variables x and y. Indirectly, the given problem, though is not expressed with 0 on the right hand side, needs to be more simplified until it reaches to the complete simplified form and then equated to 0, and thus justifying for the given example problem to be a linear or not a linear equation. This example problem, 2x minus 5y plus 4 equal to 3 minus 9x plus 2y, is a linear equation in two variables x and y. Its simplified form, its most simplified form being 11x minus 7y plus 1 equal to 0. Linear equation in two variables x and y. Now that we have discussed about linear equation in two variables x and y, let's now investigate on the solution of the linear equations. What could be the possible solutions for the given linear equation is what is the next investigation process in the coming topic. So let's see solution of linear equation. Of course, here dealing with the two variables x and y is what is the topic of the session. Solutions, as we know, are the values which satisfy the given equation, in this case being linear equation. So let's see what are the values which satisfy this equation in brief. So before we come to the understanding of the concept more stronger, let's investigate through various example problems. For example, I take 2x minus 6 equal to 0. I clearly see this to be degree 1 and degree 0. Therefore, this is a linear equation, but the number of variables is x. So this being an equation, this is an example of a linear equation in x, in one variable x. So let's recap with the linear equation in one variable and then try to understand the solutions of a linear equation with two variables x and y. So with the example problem which involves a linear equation in x, say for example 2x minus 6 equal to 0, let's see what are its solutions and how these solutions help us in understanding the solutions of the linear equation in two variables. As we can see clearly, the given equation is 2x minus 6 equals 0. Its solution is about nothing but the value of x which satisfies this equation. So let's see what value of x satisfies this equation. Clearly, when you want to identify the value of x which satisfies the equation, it's nothing but about simplifying this equation to get x. Therefore, in order to find x, I take all the x terms to the left and all the non-x terms to the right. So minus 6 does not have x, so it comes to the right as 6 plus 6. Then I have my x, which is 6 over 2, 6 by 2, because 2 comes down here, and then on further simplification I get this to be 3. Therefore, x equal to 3 is said to be the solution of the given linear equation. Is how we understand the solution. Therefore, x is equal to 3 is the solution of the linear equation in one variable x, that is 2x minus 6 equal to 0, is how I conclude. So how do we justify this in two variables x and y? For a linear equation in one variable, we can find the solution through the simple process by just evaluating the value of x, and that value of x acts as the solution of the given linear equation. But what about a linear equation in two variables x and y. So let's investigate a linear equation in two variables x and y with its solutions. So let's take an example problem of a linear equation in two variables x and y. For example, I have 2x minus 4y minus 7 equals 0. And this is clearly a linear equation in two variables because I have the variables with first term being 1 and the second term degree being 1 and this being 0. Therefore, the highest degree is 1. And clearly with two variables x and y, this is an example of a linear equation in x and y. So this is a linear equation in x and y. So let's see how we can find the solutions for this x and y. As we take here 2x minus 4y minus 7 equal to 0, let's see if we can find the value of x and y which satisfy this equation. Unlike the previous example which we have taken in the previous session, which is a linear equation in one variable x, and let's compare the solutions of the two equations. Now, as we know here, clearly I can find the value of x by taking the constant to the right and then taking 2 down, and then I get this to be the solution. Let's see if I can use the same process for my linear equation in two variables x and y. So proceeding similarly, I get this to be taking the constant to the right, as I've taken 6 to the right on the second equation, taking minus 7 to the right, I get 7, and then let's see if we can find x and y. But again, I have the variable y, which cannot be evaluated when you have the variable x. So here I clearly understand that when I have an equation in one variable, it is easy to simplify and get the solution. But when I have two variables x and y, it is not possible to find the solution x and y for this equation. Therefore, let's see how we can find the solutions of this equation in a more simplified manner. Linear equation in two variables x and y cannot be solved as we can solve for linear equation in one variable x. Can be solved, cannot be solved. So let's see what are the terms or the limitations in solving a linear equation in two variables x and y, unlike the linear equation in one variable x, which can be solved by simple mathematical process. Now let's take an example problem to understand why it is not easy to solve the solutions of a linear equation in two variables x and y, unlike for a one variable x. So here comes the example in which I would like to solve the equation x minus y equals 1. This is clearly a linear equation in one variable, in two variables x and y. When one brought to the left, it can be equated to 0. Therefore, let's see how we can solve this. Now, before we solve, it is very important to note that solving is about finding the variables. Solving is about finding x and y in this case. So we need to know what exactly x and y stand for. So in order that we need to solve this equation x minus y equal to 1, the condition is to find x and y which are real numbers. That is, we are searching for the real numbers which satisfy this equation. To find x and y which belong to real numbers is what is the target. So let's see how this target can be achieved. In order to find x and y from the equation, unlike the general mathematical process, let me try with trial and error method. Let me try with the hit and trial method. So in this hit and trial method, I first take x equals 2 and y equals 1. and let's see if this satisfies the equation. Clearly my left hand side, which satisfies x equal to 2 and y equal to 1, is equal to 1, and which satisfies. Therefore one set of solutions is x equal to 2 and y equal to 1. Let's try another hit and trial method to find the other possible solutions for this. Let me take x equals 3 and y equals 2, and let's see if this satisfies the given equation. My x equals 3 and y equal 2 implies my left hand side, which is 3 minus 2, x replaced with 3 and y replaced with 2. And we know that 3 minus 2 is 1. Therefore, even this set, because it satisfies the given equation, is said to be the solution set for the given equation. Let's try with another example. X equals 9 and x equals 8, and let's see if this is the set of solution. Substituting for x as 9 and y for 8, 9 minus 8, which is 1. Therefore, this also satisfies the given linear equation. So as you can see, there are many solutions. Like even if I take a very random number like 9,999 and I take y as 998, also equally when I replace, I get the solutions as 999 minus 998, which is equal to 1. And therefore, I get the possible solutions for x and y being 999 and 998. It continues and continues, but there is no end to the solutions for this equation. So what does we learn out of this example problem? When we see the example problem x minus y equal to 1, as we see the different sets of solutions for x and y, the different sets of solutions for x and y, all satisfying the given equation, they are all the solutions. This is a solution for the given equation. This is also a solution for the equation. This is also a solution, and this is also a solution for the linear equation x minus y equal to 1 in two variables x and y. So what do we understand? For a linear equation in two variables x and y, there are infinitely many solutions, is how we conclude with the given problem. So my learning outcome is a linear equation in two variables x and y has infinitely many solutions. The learning outcome of a linear equation in two variables x and y, it has the endless solutions, infinitely many pairs of x and y, as seen with the example problem, unlike the linear equation in one variable which has a unique solution. So we finally conclude a linear equation in one variable has a unique solution, and a linear equation in two variables has infinitely many solutions, cannot be unique. Now that we have seen the solution of a linear equation in two variables x and y, which has infinitely many solutions, unlike the linear equation in one variable which has a unique solution, let's enter into identifying the comparison between a linear equation in one variable and that of two variables, as we can do the comparison through conversion. So let's see how we can convert a linear equation in one variable into the two variable form just by using some simple mathematical process. Linear equation in one variable expressed as two variable form. Linear equation in one variable expressed as two variable form. So let's see how we can express in two variable form. So clearly we see that a linear equation in one variable p of x can be expressed in the form ax plus b. So here I write this as p of x as a times of x plus 0 times of y plus b, because when 0 is added to a term it doesn't affect. So I write this in the form ax plus 0y plus b, and hence I get this to be ax with two variables x and y, which is in this form. But this does not satisfy the condition for a and b not equal to 0, because the condition for a quadratic equation is ax plus by plus c equal to 0 with this and this. So this must be a linear equation in two variables x and y. Though this can be converted into the two variable form, cannot be a linear equation in two variables x and y, because it does not satisfy this condition. If a and b are 0, the x and y terms vanish, and hence it cannot be a linear equation in two variables x and y. Say for example, I have p of x is 3. I can write this as 0x plus 0y plus 3, because 0 when added to 3 doesn't affect the value. But since this is with two variables x and y, cannot be a linear equation in two variables, because this is not satisfying the condition a and b not equal to 0. The rules for a linear equation and its respective conditions. Condition 1 and condition 2. Now that we have discussed about a linear equation in one variable and two variables and its respective solutions and the conditions and limitations involved with the linear equations, now let's try to do some example problems to understand the concept more better. This topic is about identifying the coefficients of the linear polynomial or the linear equation. For example, I have the topic about identifying the coefficients of a linear polynomial. So let's see how we can identify the coefficients of the linear equation. For example, we have discussed in the previous sessions that a linear equation can be expressed in general form as ax plus by plus c equal to 0, with two rules. The rule 1 saying that a, b, c must belong to real numbers, and the rule 2 which says that both a and b are non-zero. So with these rules, this linear equation is about identifying the coordinates. So when I want to find the coordinate a, I clearly identify the coordinate a to be the coefficient of x. So for a given problem, if I need to identify the value of a, I pick the coefficient of x and that acts as the value a. B, the next coefficient being b, is clearly understood to be the coefficient of y. Therefore, in order that I identify the value of b in the given problem, I pick the coefficient of y and then that forms the value of b. Finally, it's about finding the constant c. So when I would like to find the value of c, I pick the constant value in the given polynomial or in the given equation, and that acts as the value c. is how we identify A, B and C. So the formula for finding A is coefficient of x, and the formula for finding B is coefficient of y, and the formula for finding C is constant. A, B, C are the constants of the given polynomial or the given linear equation, to be identified through the respective formulae definitions. Let's see an example problem to identify the coefficients in the given linear equation. Now here I have a question which says root 2y minus 4 is equal to minus 3/2x. Now here I have an equation which is given in an unsimplified form. So let's see how we can find the coefficients A, B and C for this given linear equation. So initially, for expressing this into the general form ax plus by plus c equal to 0, the first thing is about bringing all the coordinates to the left and equating to 0. So let's see how we can bring all the coordinates to the left. As I understand, this can be simplified by taking this minus 3/2x to the left, because I want only 0 out in the right hand side. So minus 3/2 when brought here reduces to plus 3/2x equal to 0. Now keeping in mind the general linear equation being ax plus by plus c equal to 0, I try to express the given problem into ax plus by plus c form. So let's see how I can express this into this form. So initially I need to have the x term, the y term and the constant, and then the 0. So let's go with the same rule. An x term 3/2x, then the y term root 2y, and then the constant equal to 0 is how we express into the general form ax plus by plus c equal to 0 in the general form. Now let's see what is a, b and c values in the given equation. As we have seen in the previous session that a is coefficient of x, therefore I clearly see that the coefficient of x here is 3/2, or written in the form 1.5 in the decimal representation. So my a is 1.5 because it is the coefficient of x. Similarly, my b is coefficient of y, which is clearly root 2, is what we get for the value of b. And my c is clearly the constant, including the sign. Do not forget to put the sign for a, b or c for the respective coefficients. Coefficients add up along with their sign, positive or negative as given. And c is the constant, which is minus 4. Therefore a is this, b is this and c is this. And finally I get my a, which is 1.5, b, which is root 2, and c, which is minus 4, is how I understand the identifying of the coefficients in the linear polynomial in two variables x and y. A is coefficient of x, 1.5, b is coefficient of y, root 2, and c is constant, minus 4. But it's very important to note that this formula is not applied directly in the unsimplified form. The rule is about converting the given linear equation into the standard form ax plus by plus c equal to 0, and then pick the values of a, b and C using the formulae as learnt. A, B, C can be found using the process. Now let's see the linear equation applied in real life. Where do we apply this linear equation concept as learnt in the class session into the outer world? Real life applications of linear equations is the topic of the session. So let's take an example problem of real life situation into understanding the concept of linear equations more better. For example, I connect this problem with the age of a person. Say, a family has father, mother and son, and let's see how this can be connected to the linear equations. So let's say the father's age (20 years more than son). So let's say the father's age is 20 years more than son and mother's age and son's age is 12 years less than 6 years less than, or let me take 10 years less than mother's age. So here I have the condition in the family. There's a father, mother and son, where father's age is 12 years more than son's age and son's age is 10 years less than the mother's age. So let's see how we can connect this with linear equations. So when we want to connect such type of real life situations into the linear equations, we try to take the given conditions in the form of x and y. Situation 1 taken with x variable and situation 2 taken with y variable. So here it's being about the age of either father, mother or son. Here comes the question on representing age of mother as x. So let me represent the age of mother to be x years and age of father to be y and age of son to be z. So father's age I represent by y, mother's age by x and son's age by the variable z. So let's see how we can connect this. Now it clearly says that son's age is 10 years less than mother's age, is how I connect between son's age and mother's age. So son's age is clearly said to be 10 years less than mother's age, and therefore I have my son's age, which is z, is x minus 10, is how I connect one equation in two variables x and y. Secondly, I have father's age, which is 20 years more than son's age, which is z. So let's see how we can connect into two variables x and y. So father's age denoted by y is 20 plus son's age, which is z, is how I connect. And then I get this to be y equals 20 plus z. So I have two linear equations and two variables x and y. Here the variables being x and z, the variables y and z. So this is a linear equation in two variables x and z as obtained through the son's age and mother's age as a real life situation. And here I obtain a linear equation in two variables y and z as a real life situation connected with father's age and son's age. Now, how do I connect the variables x and y? How do I connect the mother's age and father's age? How do I know the comparison between mother's and father's age, which is not given in this? We can do that using the linear equation concept in real life. So let's see how. So as we know the relation between mother and son's age and the relation between father and son's age, now is the question on the relation between father and mother's age, indirectly utilizing these two equations. So let's see how we can do that. Taking the second equation, which connects father and son's age, y equals 20 plus z. I have my z, which is x minus 10. So in place of z, I substitute the value x minus 10. Because I have my z, I simply substitute the value in the equation. So I get this to be 20 plus x minus 10. So z is x minus 10. Therefore, I get this to be 20 plus x minus 10, which on connecting gives me y equals 20 minus 10, which is 10 plus x. That implies y is x plus 10. So what do I understand from this? I clearly make a comparison between father's and mother's age, that the father's age, which is denoted by y, is connected with the mother's age, which is denoted by x plus 10. So I can make a comparison here that the mother is 10 years shorter than the father, or father is 10 years older than the mother, is how we connect through the linear equation. So therefore, with the equation x and y, I make a relation that implies father is 10 years older than mother. So father is 10 years older than mother. A very long gap, 10 years of difference between mother and father, connected with real life situation. Now that we have discussed about linear equations in two variables x and y with its solution concept and identifying the coefficients and the possible number of solutions for that linear equation in two variables x and y and its connection with real life situations, now comes the concept of understanding the same linear equation in graphical concept. As we have discussed about the Cartesian plane and the representation of points and the rules in the Cartesian plane, let's try to connect the linear equation with the graphical understanding. So the topic of the session is about graphical understanding of a linear equation. Graphical understanding of a linear equation. So graphical understanding of a linear equation in x and y. What is a linear equation in the graph in the xy coordinate system? How does it look, or what is its shape, is what we're going to discuss in brief in the session. For example, I take the general linear equation Pxy denoted by ax plus by plus c equal to 0 with the condition a, b, c, the coefficients being all real numbers, and a and b both not equal to 0, is how we define the linear equation in general form. So for this, how does it look in the graph is the biggest question. So when we have each of x belonging to the real numbers and each of y equally belonging to the real numbers, I see that there are infinitely many solutions, and let's see how the shape of this linear equation looks in the graph xy coordinate system. So when I draw the x and y axis with the origin, this linear equation, as it is called linear, is nothing but derived with it looks like a line, a straight line. So linear equation has its name derived from line, and hence it looks like a straight line. So any line with just randomly passing through such a line is represented by ax plus by plus c equal to 0. So a linear equation in variables x and y in the xy coordinate system is a straight line. So a linear equation graphically is a straight line. Linear equation in a graph is a straight line which I draw with a ruler, is how I understand the graphical concept of a linear equation. Now let's take an example problem to understand the graphical concept of a linear equation more better. Let's see with an example problem considered. For example, I have an equation (4x plus 2y minus 8 equal to 0) is a linear equation. So let me take this example problem to understand this equation in the graphical form. A linear equation denoted generally by L can be written as 4x is equal to 0, is how normally I represent a linear equation. Now this, when connected with graph, the first thing I do is consider the table of values. So when a linear equation is given, I take the set of values as to graph the points. So once I plot the points, I join the points, and those points will define this equation. So let's see how we can identify the points need to be plotted. So for this, I take the variable x and the variable by in each of the rows. Now in this case, I take some fixed values this. So here we understand that when I take the fixed values of 0, 0 and 1, let's see how we can draw the line using these values. So let's see how the remaining values can be filled in the table using this equation. So as we clearly see that when x is 0, we need to find the respective y. It's about substituting the value of x in the equation and then finding the other variable y, is how we understand the concept. Therefore, when x is 0, I take x as 0, and then I get this to be 4x plus 2y minus 8 equal to 0 implies 4 times of 0 plus 2y minus 8 equal to 0, which on further simplification gives 0 plus 2y minus 8 equal to 0. And therefore, this simplifies to 2y minus 8 equal to 0. which when simplified further gives 2y equal to 8. That implies y is 8 by 2. That implies y is 4. Therefore, when x is 0, I have my y, which is 4, which gets filled in this box. Similarly, when my y is 0, what will be the value of x? Is how we understand. Therefore, when I take the value of y as 0, let's see what is the value of x. My y is 0. Therefore, substituting the value of y is 0, I get this to be 4x plus 2y minus 8 equal to 0 is what we get, which on further simplification gives 4x plus 0 minus 8 equal to 0, which on further simplification gives 4x minus 8 equal to 0, and 4x is 8. That implies x is 8 by 4, 4 to the right. That implies x is 2. Therefore, when y is 0, I have my x, which is 2. When y is 0, I get my x equal to 2, which I replace in the empty box. Finally, it's about filling the last. But we just need only 2 points to sketch the line. But we just take the third point for verification, so that when x is 1, let's see what the value of y is. X is 1. 2y minus 8 equals 0. So 4 plus 2y minus 8 equal to 0. 4 minus 8 is minus 8. Now that we have discussed about substituting the value of x here, I get this equation. Through this equation, when I simplify further, I get this to be 2y plus 4 minus 8, which is minus 4, equals 0. Therefore, I get this to be minus 4, and then I finally find the value of y from this equation. So minus 4 when I bring to the right is plus 4. When 2y equal to 4, I have 2 1s, 2 2s. That implies my y equals 2. Therefore, the value of y is equal to 2, and the value of x is equal to 2, and value of y equal to 4. Therefore, for x equal to 1, y is 2 is how it gets filled. To sketch the line, it is only essential for the 2 points in the first 2 columns, but this is not required. We only take this to just verify the line, but minimum only 2 points are required for sketching a line. Sketching through only 0, 4 and 2, 0. So let's see how a linear equation can be sketched on the real coordinate system, xy coordinate system of the Cartesian plane, to be followed with. Now that we have obtained the values of x and y respectively, I have a table of x and y values which form the coordinates. As we know that a coordinate is denoted by px, y is how we denote the coordinate. It is all x values which come in the first, which is abscissa, and all the y values which come in the ordinate. So let's see how each of the coordinates are identified. So the coordinates as identified through the first column is 0, 4. The value of x, which is 0, and the value of y, which is 4. And the coordinates which are identified through the second column are b, 2, 0. The value of x, which is 2, and the value of y, which is 0. Similarly, the coordinates as identified through the third column, which is c, which is 1, 2. The value of x, which is 1, and the value of y, which is 2, is how we identify the 3 set of coordinates picked from the table. Now let's see how we can plot these points on the Cartesian plane. This is the Cartesian plane. This is x-axis. This is y-axis. and then this is origin. Now let plot through the scale of 1 centimeter equal to 1 unit. Four, 5, and this is the scale, and then comes this. So once the scaling is done for both x and y axis with 1 centimeter equal to 1 unit in this case, let's see how the points can be plotted. Initially starting with A, which is 0, 4, my x coordinate is 0 and my y coordinate is 4, I get my first point, which is out here. Secondly, my second point, which is 2, 0, means 2 units to the right and no units out, no up and down movement in the y coordinate. Therefore, my B is 2, 0, which plots out here. Similarly, my C, which is 1 unit to the right and 2 units up. Therefore, my C moves 1 unit here up, and therefore I get this to be the third coordinate. Now, as we know that these two lines when joined through a ruler, I get a straight line. The third point is only for verification that it also passes, or else this would be a wrong equation or something is wrong with the values, is how we cross-check through the verification process. So now that we got, it's about joining the line. Here is the line which I get for the given equation. Equal to 0. A line with the equation 4x plus 2y minus 8 equal to 0 is this line in the xy coordinate system. A linear equation is a straight line as given here in the coordinate system. Graphical understanding of a linear equation in x and y, a straight line, is how I understand through the learning outcome. Solutions of a linear equation. As we have discussed about the graphical understanding of a linear equation to be a straight line in a graph paper, let's see how the solutions also which can be identified or understood equally through the graphical concept. Graphical understanding of solutions of a linear equation is the topic of the session. As we have seen that the solutions are the values which satisfy the given linear equation. So let's see what values satisfy the given linear equation. Let's take the same problem as discussed in the previous session, that is the example problem. (4x plus 2y minus 8 equal to 0). And equally, this equation was identified with the linear equation y to be this, cutting the x-axis at 2 and cutting the y-axis at 4 as discussed in the previous session. Now the similar example taken is a straight line with this equation. Now let's see how we can understand the solutions of this linear equation. Now as we know that linear solutions are the values which satisfy the given linear equation. It is the values of x and y in this Cartesian plane which satisfy the given line. That is, when I take, for example, a point out here, which is 1, what is its respective y coordinate? When x is 1, clearly we identified in the previous session that y is 2. So I got this to be when x is 1, y is 2. Therefore, this coordinate is 1, 2. This is A and this is C. So let's see how we can find the solutions. So one of the solution which is identified to be B is with x equals 1 and y equals 2. So one of the solution is x equals 1 and y equal to 2. Now imagine how many such points exist on the line. As we can see this line, there are infinitely many points which lie on this line, implies there are infinitely many values of x and y on this line which satisfy the given line. That is, there are infinitely many values of x and y in this Cartesian plane which satisfy this linear equation, indirectly the line in the graph. Therefore, the line in the graph clearly proves because of the infinitely many points which makes the line, there are infinitely many solutions for the given linear equation. So graphically, it proves since a line is formed by infinitely many points x comma y, infinitely many points x comma y, therefore its respective linear equation, as in this case being this, has infinitely many solutions, is how I understand the infinitely many solutions connected with the given line. So a line has infinitely many points through which the line is created. Therefore, its respective linear equation has infinitely many solutions, x and y, belonging to R. Graphical understanding of solutions of a straight line. Learning outcome, infinitely many solutions. Now that we have discussed about the linear equations in graphical concept as a straight line in the xy coordinate system, let's see the different special cases of the straight lines, that is, the special cases of the linear equation in its own special case as a graph. Initially, I would like to know what kind of straight lines pass through origin. So the question here is, if I want to identify a linear equation which passes through origin, what would be its respective linear equation, is how we are going to investigate in today's session. So this first special case is line through origin. A straight line is said to pass through origin if it has its constant 0. So let's see in brief about a line through origin. For example, I have x-axis and y-axis. So I wanted to just identify a line which passes through origin. Passing through origin. So when a line passes through origin, what would be its equation? How does the linear equation look like? So in this case, a linear equation would be in the form y equals kx, is how I understand. A line passing through origin has its linear equation in the form y is equal to kx. A line passing through origin always has its linear equation in the form y is equal to kx, or it can also be written in the form p of xy ax plus by equal to 0, is how I understand a linear equation passing through origin. The learning outcome out here is that when a line or a linear equation passes through origin in the xy coordinate system, its constant value vanishes. Therefore, if I have the general linear equation ax plus by plus c equal to 0, this constant vanishes when it passes through origin. Therefore, a line which passes through origin would be in the form ax plus by equal to 0, with ab belonging to real numbers and ab both non-zero, is how I understand the special case of a line passing through origin, which can be expressed in the form y is equal to kx or ax plus by equal to 0. Ax plus by equal to 0 with the conditions ab being real numbers and ab both non-zero. Let's see an example problem in the continued session. For example, when I want to identify a line passing through origin, if suppose I have y equals 2x, then clearly this is in the form ax plus by. So in order to identify whether this line is passing through origin or not passing through origin, I first try to reduce this into the general form with the condition a line passing through origin must have the condition ax plus by equals 0. Therefore, y equals 2x implies this can be written as 2x equals y, and therefore this y when brought to the left is written as 2x minus y equal to 0. Clearly, as I see the comparison, this can be written in the form ax plus by equals 0, which says that since the constant value is 0, since 2x minus y equal to 0 does not have a constant value, therefore this must pass through origin, is how we conclude. Since this does not have a constant value, therefore 2x minus y equal to 0 passes through origin. It should be a line which passes through the origin in the xy coordinate system. A straight line passing through origin represented by ax plus by equal to 0. See the constant vanishes, is how I understand. Now that we have seen the linear polynomial y is equal to kx, which has its own graphical properties passing through origin. Now let's see one example problem to understand the concept more stronger. Imagine I have a line y is equal to 3x, or I take y is equal to 2x. And my question out here is to sketch y is equal to 2x on the Cartesian plane. So let's see how this linear equation in two variables x and y with its special case looks in the Cartesian plane. Now, as we know that the given equation is y is equal to 2x, where the constant c is missing, it's clearly in the form y is equal to ax plus b, where b is 0. I mean ax plus c or ax plus b, where the constant is 0. Therefore, this line must pass through origin in the form y equals kx. So this line passes through origin is how I understand the concept of the given example problem, y equals 2x, a linear equation in two variables x and y without the constant as a special case. Now, in order that I sketch this, the first thing which I take into the rule is about the table of values. Now, as we know that to sketch the line or to make a line, it is minimum of the 2 points which are required. So, if I have 2 points which can be identified for this line, which lie on this line, then it's easy to sketch the line. The minimum conditions for a line are 2 points. My first row with variable x and my second row with variable y. When x is 0, my y is also 0, because when x is 0, my y is 2 times of x, which is 2 times 0, and this is 0. Therefore, when x is 0, the y coordinate substitutes to get the value 0. Similarly, if I take another value, say 2, when x is 2, my y is 2 times of x, that is 2 times of this 2, which is 4. Therefore, when x is 2, my y is 4, is how I understand the sketching concept through the table of values. Now that for 2 points, I have got one of the point as represented by the second column and the other point represented by the third column, I clearly understand that there are 2 points P which is 0, 0 and the points Q which is 2, 4. That is the points P 0, 0, that is the origin, and the point Q which is 2, 4 pass through the given line y equals 2x. So let's see how we can sketch utilizing these two coordinates as evaluated through the table of values. Now that we have evaluated the values of P and Q which lie on the line y equals 2x, let's see how we can sketch the line utilizing these two coordinates on the Cartesian plane. So initially, I'm going to start with sketching of the Cartesian plane. Cartesian plane with x-axis and y-axis. The horizontal axis, which is x-axis, and the vertical axis, which is y-axis, and the point of intersection, which is the origin. Clearly, let me first make a scale of 1 centimeter equals 1 unit on x-axis. So here is 1, here's 2, here's 3, here's 4, 5, 6, and etc., so on and so forth. And on the left, I have -1, -2, -3, and -4. Similarly, I take a scale of 1 centimeter equal to 1 unit even on the vertical axis, that is the y-axis. 1, 2, 3, 4, 5, and similarly the values on the negative side of the y-axis being -1, -2, -3, -4, and so on and so forth. So with this scale of 1 centimeter equals 1 unit on x-axis, and equally the 1 centimeter equal to 1 unit also on the y-axis, let's see how we can sketch the points. Starting with point P. The point P is origin, that is the initial point 0, 0. Therefore, I see that this point clearly is the origin which is fixed here. So my point P is out here. Coming to the next point, point Q is 2, 4. That is, the point moves 2 units to the right from the initial point, 2 units to the right from initial point, and 4 units up from there. Therefore, once I reach 2 units to the right from its initial position, I jump 4 units to the top. Is how I get the point Q, which is 2, 4. Is how we get the point Q and point P in the Cartesian plane. Now, as we know that to draw the line, minimum 2 points are essential. Now that we have got the points P and Q in the Cartesian plane, it's about sketching the line. Sketching the line is about joining the 2 points and extending the line on the either side. So here I just join P and Q and extend in this manner. So I get this to be a line which is extended on the either side and equally passing through P and passing through Q, both the points as obtained through the line y equal to 2x. Therefore, the line as obtained passing through P and Q clearly is witnessed to have been passing through origin. So what do we make the learning outcome? The biggest outcome here is that if the line y equal to 2x is expressed in the form y equal to kx, then that line must pass through origin. Therefore, a line y equal to 2x with the points 0, 0 and 2, 4 as picked and on random choice are just located on the Cartesian plane here and here, and when a ruler is taken and you draw a line, it passes through P and Q and we obtain this line. And this line, as it is represented by the arrows, is nothing but the line y equals 2x. And importantly, this line expressed in the form y equal to kx passes through origin. It must pass through origin because it does not have a constant. No constant must pass through origin. A constant, then the line does not pass through origin. So a constant plays a vital role in deciding whether the line passes through origin or does not pass through origin. Y equals 2x passes through origin is the learning outcome in this problem. A, y equals ax plus b does not pass through origin if b is not equal to 0. The condition is this line does not pass through origin if b is not equal to 0. If b is equal to 0, then this reduces to the form y equal to kx or y equal to bx, and the line must surely pass through the origin. B, the constant, decides the factor for the line passing through origin and not passing through origin, as seen through the example problem y equal to 2x. Now that we have taken the case of y equal to kx, which passes through origin, as a special case, let's get into the next special case in case of the linear equations in two variables x and y. In this case, being x and y. So let's see the case number 2 in the topic of the session. Now before we start with this, let's try to analyze what happens if the line is parallel to x-axis. There are chances of lines not always passing through origin or not passing through origin, but different cases where a line is exactly parallel to x-axis or a line is parallel exactly to y-axis. So let's go into investigating the cases of lines parallel to x-axis and parallel to y-axis accordingly. Line parallel to x-axis. So let's take the first case of a line parallel to x-axis. What would be the equation of a line parallel to x-axis is what is the investigation in the session, today's session. Let me take a Cartesian plane to investigate a line parallel to x-axis and its respective form. So I take the x-axis and the y-axis and the origin. Now let me take a line which is exactly parallel to x-axis. Parallel in the sense any line I draw along the parallel to x-axis in the sense it is at equal distances at every pair of points. That is, when I take a line say I take the line this which is assumed to be parallel to x-axis. Now this is parallel only when each of the distance as taken, the perpendicular distance between any 2 points on the 2 lines are equal. So imagine I take this distance and this distance. If they are equal, then I say the lines are parallel. Equally at distances, equally at equal distances. It cannot have unequal distance at any stage of its parallelity is how we understand parallel lines. Therefore, let me say the line L is parallel to x-axis. The line L is parallel to x-axis. This is the representation for parallel. So line L is parallel to x-axis. So let's see what would be its equation and its investigation. Imagine I have this line which cuts y-axis at k. So imagine that this line cuts y-axis at exactly the distance of k units. This is how I understand the distance of the line from x-axis to be k units. Now let's see what would be the equation of line. Now let me just take randomly any point out here. Say for example, I take the point P which cuts y-axis. P is the point where the line cuts x-axis. Point where, the line cuts y-axis. Point where L cuts y-axis. Therefore, the coordinates of P, because this is the y-intercept, simply because it cuts the y-axis, the line cuts the y-axis at the point P, P must be the y-intercept. If a line cuts x-axis, then that point will be the x-intercept. If the line cuts y-axis, then that point of intersection is called y-intercept. So P is the point where the line L cuts y-axis, as clearly seen out here in the diagram. Point where L cuts y-axis, which is 0, k, because the distance from O to P is k units, as can be seen clearly in this diagram. So this being k units, I have this to be 0, k is how we get the coordinates. Next, let me take the general form of the line. The general form of line L, which we know is represented in the form ax plus b. Or ax plus by plus c equal to 0 is how we get the general form. So let me take the general form ax plus by plus c equal to 0, where the condition, we know that a, b, c are real numbers and a and b are not equal to 0, is how we have discussed about the general equation of a line or linear equation in two variables x and y, which can be represented in its general form as ax plus by plus c equal to 0. Now, since this line passes through the point P, the coordinates of the point P must satisfy the given equation, is how we understand the representation of the line through the point 0, k. Therefore, P lies on L. Since P0k lies on line L, therefore this must satisfy the line L. Therefore, P satisfies line L. That is, the coordinates of the point P satisfy the line L. Let's see how we're going to satisfy the line through the coordinates. Now let's see the formula. What is the condition for the line L parallel to x-axis? So here comes the formula. Any line L, this line may be anywhere in the Cartesian plane, provided the condition that this line is parallel to x-axis. So any line L which is parallel to x-axis, here being the line L. So any line L which is parallel to x-axis is of the form y equal to k, is how I understand the formula, where k is the y-intercept, or k is the distance from the origin to the line L, or the distance of the point on x-axis, or the distance between the line L and x-axis. Therefore, any line parallel to x-axis must be of the form y equals k, k being the y-intercept, the point where the line cuts y-axis, the y-intercept. So this is how we derive the formula, where any line parallel to x-axis is of the form y equals k, understood through the formula. Now let's see an example problem to identify the line which is parallel to x-axis through the given formula. Now let's see an example problem to understand the concept more better. The question here, which says, find the equation of the line which is parallel to x-axis and at a distance of 3 units below x-axis. Now here I have a question which has the various conditions taken into account. For example, the question here is find the equation of the line which is parallel to x-axis and which is at a distance of 3 units below x-axis. So let's see how we can identify the line through the given conditions. So before we do this problem, we need to analyze the given conditions through the Cartesian plane. Without the Cartesian plane and the display of this information on the Cartesian plane, it is impossible that we can solve this problem or any mathematical problem. Display the information in the Cartesian plane is the demanded condition out here. So let's see how we can convert this into the Cartesian plane. The Cartesian plane, which consists of x-axis and y-axis intersecting at origin, x dash and y dash intersecting at origin. Now the question says we had to find the equation of the line which is parallel to x-axis. The condition which we have seen in the previous session is about that any line which is parallel to x-axis is of the form y equals k. What's k? K is the y-intercept, or the distance of k is the distance between the x-axis and the line, the perpendicular distance. So let's see which is the line which we need to find is said to be parallel to x-axis and at a distance of 3 units below x-axis. Now since the line is 3 units below x-axis, I obviously take the line below the x-axis. So as we take the scale 1, 2, 3, 4, 5 and 6, and then I have my scale here -1, -2, -4, and then I have 1, 2, 3, 4, -1, is how we get the scale taken as 1 centimeter equal to 1 unit. Now since the line is 3 units below x-axis and exactly parallel to x-axis, it moves 3 units down and I have a line which is out here. Which is like this. So here is the line which is parallel to x-axis and at a distance of 3 units from x-axis is how we understand below x-axis. Now in order that we find the line, we know that any line which is parallel to x-axis, say this is the line L, so L parallel to x-axis implies y is equal to, the line L can be expressed in the form y equals k, because any line parallel to x-axis is of the form y equals k. So this can be expressed as y equal to k, and k is the y-intercept. My k out here is the y-intercept. Now as I know my y-intercept out here is -3, therefore k is -3. As clearly seen, my line cuts y-axis at -3. So my value of y-intercept, that is k, is -3. Therefore, substituting k equal to -3 into this form, I get this to be y equals -3. Therefore, the equation which I demand for is y equals -3. Therefore, for the given question, the equation of the line which is parallel to x-axis and at a distance of 3 units below x-axis with a distance of 3 units, which is below x-axis, is y equals -3. Is how I conclude with the line parallel to x-axis. Now that we have taken the condition of a line parallel to x-axis, the next question which arises is about what is the situation when a line is parallel to y-axis. So today's investigation in the session is about a line parallel to y-axis. What would be the formula if the line is parallel to y-axis? Let's start this with the Cartesian plane. The Cartesian plane, which is x, y, x dash and y dash, intersecting at origin and then let's take a line which is parallel to y-axis. Say for example, I have a line this is the line L which is parallel to y-axis. Now let's see what will be equation of this line L. Imagine this line cuts x-axis at k, just like the same line cutting y-axis at k when it is parallel to x-axis. Similarly, if the line is parallel to y-axis, it must cut x-axis, but it never cuts y-axis. So it cuts x-axis at say k. Now the question comes, what would be the equation of this line L? So let's see how we can just derive for this formula. Any line L which is parallel to y-axis and cuts x-axis at k, that is the distance from origin to k is k units, is how I understand the other way. So geometrically, this distance is k units, that is the distance of the line from y-axis is k units, is how I understand the concept. So any line L which is parallel to y-axis and cuts x-axis at k, in this case the line being L dash, that line is of the form x equals k, is how I understand the formula. Any line parallel to y-axis and passing through k, cutting x-axis at k, that is when the x-intercept is k, then the equation of the line L is of the form x equals k. Line parallel to x-axis, y equal to k. Line parallel to x-axis, y equal to k. Line parallel to y-axis, x equal to k, is how I understand the concept. Let's see an example problem to understand the concept more stronger. Let's take an example problem in which I need to find the equation of the line parallel to y-axis, the special case of linear equations in two variables x and y. Imagine I have an example problem which says find the equation of the line which is parallel to y-axis and makes an intercept and makes an intercept 3/2 units. So here I have a question with its respective information, which I'm going to convert into the Cartesian plane. And through the Cartesian plane, I can find the equation of line accordingly through the respective formula. So let's see how I can display the information as given in the question into the Cartesian plane. The question is about finding the equation of the line with the condition that it is parallel to y-axis and makes an intercept 3/2 units. So let's see how it makes an intercept. So as I take the Cartesian plane with x and y-axis intersecting at origin, let me just take it with a scale of 1 centimeter equal to 1 unit on x-axis and 1 centimeter equal to 1 unit on y-axis. This is -3, -4, and so on and so forth. And the scale on y-axis is 1, 2, 3, 4, and then -1, -2, -3, and so on and so forth. Now clearly it says the line is parallel to y-axis and it cuts and it passes through the intercept 3/2 units. So initially it is very essential that we locate the x-intercept, which is 3/2 units. Now here is 3/2 units is the x-intercept indirectly 3/2 units is 1.5 units is how I understand the x-intercept. So using the condition of x-intercept being 1.5 units, let's see how we can draw a line passing through x-intercept and parallel to y-axis. As we know that the value 1.5 units is clearly located at in between exactly the middle of 1 and 2, this is the x-intercept. And of course, the line passes through this point exactly in the middle of 1 and 2 and parallel to y-axis is how the question is analyzed through the Cartesian plane. So let's draw a line parallel to y-axis and passing through the x-intercept 1.5 units. This is the line. L dash is the line which passes through the x-intercept. L is parallel to y-axis and L passes through x-intercept equals 1.5 units. Therefore, the line L passes through the x-intercept, which is 1.5 units. So let's use the formula. Now comes the importance of the formula. As we have seen in the previous session that any line parallel to y-axis and passing through k units being the x-intercept is x equal to k, and therefore my x-intercept, which is k, is identified to be 1.5 units, and therefore line L dash is given by x equal to k, that implies x equals 1.5. So the equation of the line which is parallel to y-axis and passing through the x-intercept of 3/2 units, which is 1.5, is given by x equals 1.5 is how we identify the equation of a line parallel to x-axis and parallel to y-axis as the special cases. The special case of linear equation in two variable x and y, line parallel to x-axis and line parallel to y-axis. Now comes the question on the linear equation which can be sketched on the Cartesian plane. What if the line is given on the Cartesian plane and I would like to find its equation? I am talking about the reverse process of understanding the line and its graph. So let's see the investigation in today's session about how we can identify the equation of the line which is on the Cartesian plane. The reverse process of understanding the line through the graph. So let's see the concept. The reverse process here is, given the line in Cartesian plane, finding its equation is how we are going to identify through this. So let's see how we can identify the line through its, identify the equation of the line through its line in the Cartesian plane. Let's see how we can investigate. For example, I take the line which is in the Cartesian plane to investigate through its equation which needs to be identified through the plane and its line. So let me take the Cartesian plane x dash and y dash. Now let me take the scale on x-axis which is 1, 2, 3, 4, 5, 6, -2, -3, and this, and then along y-axis which is 1, 2, 3, and this. Now let me take a line on this Cartesian plane. Imagine I take a line with this and so on and so forth out here. So I get the line passing through say this. Here is the line. Here is the Cartesian plane. Now my question is, what will be the equation of this line? Is how I understand the reverse process of understanding that given the line in Cartesian plane, how to find its equation. So let's see how we can find the equation of this line L. Now here I have a Cartesian plane in which the line lies here. As clearly this passes through origin, the first thing I identify that this line L must have the equation y equals kx, no doubt. because it passes through origin. It must be of the form y equals kx. And similarly, as I see that every x coordinate, when x is 2, I identify its y as 1, which I identify. Now when x is 4, I see that my y is 2. Similarly, when I take the third point, when x is 6, my y is 3. So I try to identify a pattern between the x values and the y values. So clearly I see here that 1 is always, when I write this in the form 2 by 2. Similarly, when I have y equal to 2, indirectly it is nothing but 4 by 2. So this 4 coming into the numerator. Similarly, when I have y equal to 3, which is obtained from the third point, it is nothing but in terms of x, which is 6 by 2, provided this gets connected with this. Clearly we see that in this, every y value is half of the x value. That implies every y value on L is half of its x value, as clearly seen in this investigation, which shows every y value on line L is half of its x value. Therefore, my every y mathematically is half of x, is how I identify. Therefore, I got an equation which is y equals x by 2. Therefore, equation of line L is y equals x by 2 is how I understand. Equation of line can be identified through its line in the graph. This line in the graph in the Cartesian plane is with its equation y equal to x by 2, investigated through its x coordinates and y coordinates, which gives me the condition. Reverse process of understanding the equation of line through its Cartesian graph. Now that we have discussed about linear equations in two variables x and y, let's try to apply in real life and see the application of a line in real life situations. There are many situations which demand for linear equation, like speed, velocity, all are related to the linear equation. Velocity time graph is a linear equation, etc. So let's see more of real life applications of linear equation through one of the real life situation. Now, as we have seen that in lower classes we have learned the conversion of centigrade to Fahrenheit, the temperature conversion which you have learned about centigrade to Fahrenheit or Fahrenheit to centigrade is what we are going to see as a real life situation. For example, real life applications of a line or a linear equation. Let's see how we can apply this in real life situation. For example, I have temperature conversion equation. Usually we have the temperature conversion which is done through the mathematical calculated equation through the data collection, which is given to be F equals 9 by 5 C plus 32. temperature conversion equation F equals 9 by 5C plus 32 is what is the linear equation in X and Y. So using this temperature conversion equation, F equal to this is used to calculate initially the foreign heat when C is 30 degrees, and secondly the centigrade when the foreign heat is 12 degrees. So let's see how these conversions can be done for the given real life situation. So I have in the initial case the centigrade degree which is given in the temperature of 30 degrees, through which I want to know its respective foreign heat temperature. So for this centigrade temperature, I would like to find the temperature in F, its conversion in foreign heat scale. So let's see how we can do that. The given conversion equation, the linear equation, is F equals 9 by 5 C plus 32, which is clearly in the form y equals ax plus b. Here F is assumed to be the y coordinate and C is assumed to be the x coordinate, where y equals 9 by 5x plus 32. That is, when I take the x-axis and the y-axis, this is foreign heat, this is centigrade which comes in x-axis, and the foreign heat which comes on y-axis, is how we understand graphically connected with C and F, C for x and F for y. The foreign heat is 9 by 5 plus C plus 32. My question 1 demands for finding F. To find F when C is 30 degrees. The value of C is 30 degrees, which when substituted in to the given problem, F equals 9 by 5 times of C plus 32. So the value of C as given in the question as 30 degrees substituted to be 9 by 5 times this plus this, which on further simplification gives us 5 ones, 5 6, 6 nines, 54 plus 32. 86. Therefore, my F is 86 degrees Fahrenheit. So 30 degrees centigrade converts to 86 degrees Fahrenheit out here. Is how we understand the conversions which can be done given the linear equation y equals ax plus b, y for F and x for C. Next, let's see the next problem about finding C when F is 12 using the same linear equation. Secondly, my second part is about finding C. So to find C, let's see how we can find the centigrade temperature for the foreign heat. F is given to be 12 degrees Fahrenheit. That implies when I substitute into the given equation, 12 is 9 by 5 times C plus 32. So when F is 12 degrees Fahrenheit, I convert by substituting to F equals 12 and then simplifying to find C. Now it's about finding C, so I take this to the left hand side. 9 by 5 C plus 32 is 12. That implies 9 by 5 times C is 12 minus 32, 32 comes to the right as minus 32. That implies 9 by 5c is 12 minus 32 is minus 20. And then which on cross multiplication gives us 9c is 5 times minus 20, which on further simplification gives us 9c is minus 100. That implies c is negative 100 by 9, which approximately converts to minus of 9 ones 9, and then 10, 9 ones 9, and then 10, 1 1. So approximately c is negative 11.1 degrees Fahrenheit is how we understand the conversions as done through the Fahrenheit. So F equals 12 implies C equals negative 11.1 is how we can find the values of the temperature conversions using the linear equation. My next question here would be, when will the two temperatures be equal? Is there any possibility to find when the centigrade and Fahrenheit scale reach to the same value? So let's see if we can identify the temperature at the break-even point. That is, at the point where the two temperatures C and F are equal. So let's continue with the continued question out here. So my next question out here is, when will the two temperatures F and C, when will the two temperatures on F and C scale meet is my question out here. So when do they be equal? Let's see if we can find that point where F and C are equal. In order that we do this problem, it is very simple that we assume that the two temperature scales are equal and then find the value. A reverse process of working out. So assuming that F equals C, let's try to find the value utilizing, of course, the linear equation. Real life applications of a line. Now that F equals C, I substitute F equals 9 by 5 of C. So my F being C replaced with C plus 32. So here my F gets replaced with C. Is how I understand the substitution. Now let's find the value of C by taking all C terms to the left. So here I get this to be 9 by 5 times C plus 32 is equal to C, which on further simplification gives 9 by 5C minus C equals negative 32. 32 comes to the right as minus 32, C goes to the left as minus C. So taking the LCM, we get this, which on further simplification gives 4C by 5 is minus 32. That implies C is 4 ones, 4 eights, so minus 8 times 5. Therefore, C is minus 40, and F equals C implies is how I can identify the values of F and C being equal to 40. Therefore, when the temperature reaches 40 degrees centigrade or 40 degrees Fahrenheit, the two temperatures meet on the same scale. that is 40 degrees centigrade is exactly equal to 40 degrees Fahrenheit. Only at 40 they both are said to be same. 40 degrees centigrade equals 40 degrees Fahrenheit is how I understand the applications of line in real life situations. Temperature conversions being one of the real life application. Let's reconsider the example problem f equals 9/5c plus 32, the temperature conversion formula in its linear form. If my question was to draw this, clearly this is a linear equation in two variables f and c. This is a linear equation in f and c. Therefore, this must be a straight line. Its graph is a straight line. That is, when I take this on x-axis and y-axis, my centigrade scale on x-axis and my Fahrenheit scale on this gives me a line with y-intercept cutting at 32, and my slope is positive, so it cuts X-intercept. X is 0. When yf is 0, I get minus 32 somewhere out here. So this is how I get the line when I sketch on the xy coordinate system or FC coordinate system. A line in its temperature conversion is a straight line in the Cartesian plane, as can be drawn using the table of values. Sketching a line for a real life situation.